and welcome to this video. Now, some while back, while I was charging my power bank, I started seeing smoke coming out of the power bank. So I decided to open the power bank, and after I checked the board, I found out that this chip here was fried up. So the easiest way would have been to get another of this power bank board, but this is not China. You can't easily get board for this power bank exactly. So I thought to myself, instead of me looking for the board up and down, why not use electronic skill to build a board? Why not design a power bank panel from scratch? So that's what I'm going to be doing in this video. In this video, I'm going to be building a power bank circuit from scratch, because if we check the power bank, the battery is still functioning well, and the battery is is in between 3.7 to 4.2 volts. So since it's still working, we are going to be looking for a circuit which will convert the 3.7 volt to 5 volt, because if we should connect the 3.7 volts directly to our phone, it won't charge. Although I did say that I'll be building a power bank panel circuit from scratch, but why should I reinvent the wheel when I can just make the wheel better? So what I did was I went to Google and searched for 3.5 to 5 volts converter circuits, and these are the boost circuits that I got. So after navigating through the circuits, you can see here this one is saying 3 volts to 5 volts, but the issue is we may not be able to get this AC. So this one is out. So and they are talking about module, and also this one is the ideal circuit for a boost converter. So this is how a normal boost converter will look like. So this one here is the circuit that we are going to be working on. This is the full circuit here. You can see the 555 timer. All these components can easily be gotten around. So after some tweaking, I came up with this circuit. As you can see here, this is the circuit here. So this circuit is basically divided into 3 sections. First of all, we have the battery section here. This is the lithium-ion power bank battery. Here, from here like this to this place is basically the oscillation section, and is what is responsible for on and offing of this transistor here. And from here to here is the output section. So we are going to be explaining now. Let me explain how the circuits work and how come about all of this resistance value here. Now, before we explain how all of those circuits work, let's take a short while to explain how a basic boost converter circuit simply works. So this is how a basic boost converter circuit looks like. You have got your input voltage here, your inductor, your capacitors, your switch, your diode, and your output voltage here. Now, to answer the question, how does a boost converter convert a low voltage into a voltage higher than the input voltage? Well, you can think of it as this way. If you have 1.5, let's just say a 1.5 volt battery, two of them, and you need a 3 volts, let's say for a 3 volts. So how do you do that? How do you get your 3 volts? You get your 3 volts by simply connecting the 1.5 volts, two of the 1.5 volt together in series, and that is exactly what a boost converter do. Take for instance, this is your input voltage, but if we look closely at this boost converter circuit, you can see that we don't have any battery here, but we have an inductor here. This is because this inductor here is here to store the charges, like it's acting as a battery. So whenever we close this switch here, one end of this inductor gets connected to this ground, and whenever we open the switch, that charge that is being accumulated in the inductor is being added in series to the input voltage here. So how long do we keep the switch off affects the output voltage, and how long we keep the switch on or off is called the duty cycle. And also how fast you close it and or open it is called the frequency, and that also determines the output of the converter. Now to determine how long and how fast we have to close this switch here, there are some formulas that we can use to know that. But in this digital age here, using all of those formulas may consume time, so that is why we use this online calculator here. So as you can see, if you enter a frequency range, say 20,000 Hz, that is 20 kilohertz, minimum voltage that we expect in 3 volts, maximum voltage 4.2 volts, and the minimum V out, that is 5 volt output voltage, and the current. So after we input all of those data, we will press calculate, and it will give us the duty cycle that we need. So if you can look here, we have 41%, so we can just assume a 50% duty cycle. Also here we have the inductor value, which is almost close to 10 microhenry. We use a 10 microhenry here. We also have our capacitor value. Is all of these values that we use, since we have NE555. Look at the NE555 here. This is how we wire it in order for it to be opening and the close to be acting as the oscillator here. You have the R1, R2, and the capacitor. So for us to get these values of resistors and capacitors, you come down here. What we got then, we get a frequency of 20,000 Hz, a duty cycle of 50 Hz. So after inputting it, to then now calculate the combinations of the resistors and the capacitors that we can use. So let's just use this 680 nanofarad, 1 kilo ohms, 47 kilo ohms, and this, since this one here is almost close to what we have, so we will use this value here. We'll pick 680 nanofarad, 1 kilo ohms, and the 47 kilo ohms, and that's what we put here in our circuit here. So these are the values of the resistor. Finally we have our output section here. As you can see, you can't find any phone here, but we are using this resistor to represent our device. The reason why we choose this 5 ohms here is because we already know that the voltage that will be coming here is 5 volts and the current should be 1 amperes. So from Ohm's law, if we calculate it, you can see V is equals to IR. Our V is 5, our I is 1. So if we divide it, we come up with this 5 ohms resistor. So if you are, so that is how the whole circuit work. So now let's run the simulation and see if it's working. So as you can see, we are getting up to 5 volts here, and this is the current that is flowing through it. So now that we have our circuits up and running, let's try to simulate a scenario. And this scenario is if you decide to unplug your phone and plug it back. So with that, what we are going to do is let's disconnect this resistor here, which represents our phone, and let's run the simulation again. So as you can see here, the voltage here is ramping up to, so the voltage here is reaching above 40 volts, and if we are to plug this voltage directly to our phone, it will destroy our phone. So in order to solve that, let me stop the simulation, pick device. We are going to use a voltage regulator. So what a voltage regulator does is, by any voltage that is higher than the voltage of the voltage regulator, it will simply limit it. So as you can see the description here, 5 volt fixed 1 amp possible positive power supply. So any voltage that is above 5 volts, it will limit it to 5 volts. So let me add it my circuits and see what will happen. Here, pin 1 is V in here. This in, connect the ground. Let me connect the multimeter to it. So as you can see, even as the voltage here is reaching 30 or 40, even as the voltage here is increasing, this voltage at the output here is still maintained at 5 volts. It's not even shaking at all. So that is the work of a voltage regulator in a circuit. So what this simulation simply means is that if you bought all of these components, you got all these components and you connect them together in this way, it simply means that your circuit is going to work. So the reason why we do simulation before building the final circuit is because you want to know whether it will work or not, whether the components, you need to know the component that you are going to purchase, so that you won't be wasting money buying components, building a circuit that won't work. With that, I come to the end of this video. See you in the next video.